Hello, today I'm going to be doing an example of an open system featuring a turbine and an ideal gas. If you want to follow along, this is going to be on chapter 5, 152. So, this problem features a turbine running an ideal gas, like I just said, with some work out. The objective of this problem is to find the volume flow rate at the inlet. Right? And so to start off this problem, we're going to do a dotted line that represents the control volume, meaning that we will take the energies around that control volume. Right? And we have to assume some things as well. First of all, it's taken right off, but we can say that this is an ideal gas. The CP and CV are given in the problem, so I guess it's safe to assume this is constant specific heat is what they're giving us, and it says that this is at that CP and CV are taken at average temperature. Right? They didn't give us what the name of this ideal gas is, so this is the best they could do. And as you can see, this problem does not give us any type of kinetic or potential energies, so we can say KE and PE are negligible. Sorry, this says KE and PE are negligible. And last but not least, we have this we don't have any heat, so like I said before, if it doesn't give us any indication of whether there's Q in or Q out, we can just assume that this is an adiabatic turbine. Okay, so the next thing to do after this is always the energy balance. So this is the energy balance for an open system. E dot in minus E dot out equals change E dot of system. This always goes to 0 because this is a steady state flow system, meaning that the energies at any point within this turbine will always remain constant. So just subtracting them would be 0. So then we do this goes to E dot in equals E dot out. All the ins and all the outs you can have. We can have Q dot in plus work dot in plus M dot times H1 plus V1 squared over 2 plus GZ1. I'll write this down here. Equals Q dot out plus work dot out plus M dot H2 plus V2 squared over 2 plus GZ2. Right? So after this, we can just start subtracting what we don't need. So we know this is we said that K and P are negligible. It was an adiabatic turbine. So turbines only have work dot out, so there's no work in, and we're left with this equation. It might also help to know that we're also given this work dot out, which I'm sorry I didn't give you in the first place, but that's 650 kilowatts. So after this, we can just narrow down our energy equation, and this will look like here. M dot H1 is equal to work dot out plus M dot H2. So if you can't see this, all right. And so then after this, well, we want to find the volume flow rate. We do have this workout. We can find this and this somehow. I'll show you that right now. But this mass flow rate is unknown. And for this problem, probably to find this volume flow rate, we know that the volume flow rate is actually a function of mass flow rate where this is equal to m dot times specific volume. So to do this, well, let's rearrange this further here, right? So we'll have the workout here, and let's do this. Let's just write it how we would normally go about it. It's workout is equal to m dot h1 minus h2. This is a ideal gas. An ideal gas with constant specific heats, so we can change this, and so this will become w dot out is equal to m dot, where this is Cp T1 minus T2. We need to get m dot by itself. M dot is equal to work dot out over Cp T1 minus T2, right? And so in the previous problem, I already supplied all these values, and you should get the number or the mass flow rate of probably about 1.44 kilograms per second, something around there. And knowing this mass flow rate, well, we just said that volume flow rate we can express as mass flow rate times specific volume. And the reason that is well, I said this, and this could be written as what this is kilograms over seconds, and what we want is in meters cubed per second. This is in meters cubed per kilogram, right? And you see how that works. These kilograms, you have meters cubed per second, right? And basically all I did to find this equation was kind of some unit analysis. You can also go about it by mass flow rate is equal to, by just listing all your mass flow rate equations out and deriving it that way. So our next goal is to find this specific volume at 1, right? Because we have the mass flow rate, we want the volume flow rate at 1. So we would need to, in order for this to be true in the sense that v cross 1 is equal to m dot times v specific volume 1, we need to find the specific volume. And in fact, the way to do that is something we always forget about most of the time, that we can use when we have an ideal gas, and that is the ideal gas equation, which says PV is equal to mRT. We're just going to kind of modify this for the open system and the fact that we want this specific volume flow rate. So P specific volume is equal to RT. So with this, now we can actually get the answer, and specific volume 1 is equal to RT1 over P1, right? And so knowing this, we can now kind of calculate this volume flow rate. Putting in the values, you should get something around 0.4 meters cubed per kilogram. The final step obviously would be to input the mass flow rate we found and the specific volume flow rate we found. And this will yield an answer of 0.575 meters cubed per second.